So let's proceed to the second part of our discussion. In the first part of my discussion, actually, I'm just talking about why we need our symmetry transmission line to be open circuit at a certain frequency. And because we want to make the building block become invisible. And let me just use these three design examples as an illustration to demonstrate the design procedure. Actually, at the first grade, okay, when you're looking at the topology, you will get an image. And many people ask me, are you just designed this synthesis transmission line using a fine-tuning, using a completed tuning process? It seems like because they are just arranged very strangely, a complicated way to integrate the component. So many people ask me the question: Is you or your group, does your group to design this sort of symmetry transmission line completely based on the tuning process? My answer is no. Actually, we did not design such kind of a synthesis transmission line using a tuning process. Actually, each time we have something in mind. For example, we at a certain frequency, for example, 2.5 gigahertz, we would like our transmission line to be 35 ohm and 90 degree, for example. And at 5 gigahertz, we would like to have our line to become open circuit. Then we start our discussion, always start our design using the alias, not the HFS or the CST, just using the alias. And using the alias, using ideal component. Ideal component means like the components without loss. Okay, just forget about loss, just using the ideal component. And have some circuit topologies in mind. For example, we will have a pi network. For example, we will have a 5 ladder type network or something else. Okay, and then using this spatial kind of network, we can draw a certain topology of the circuit, and then perform the simulation and fine-tune. No, actually, then the next step is to derive the equation. We can derive several equations. For example, let me just take, for example, these cases. I will use these cases as an example. Okay, we have something in mind. We have three conditions. At a certain low frequency, its characteristic impedance must be equal to 35 ohm. And at the same frequency, the electron length must be equal to 90 degrees. And the third condition is at a higher frequency, the characteristic impedance of a line must become 50 ohm. So actually we have three conditions. And just think about these topologies. Just ignore the connecting line. We actually have no. In a connecting line should be taken into account. Actually, just think about the connecting line and also think about the whole topology. It is just actually a simple pi model. And for this pi model, actually, we have two unknowns. The first unknown is the inductance, right? It is inductance. And the second unknown is because actually they are just for layout purpose. So they are separate to two capacitors, but actually they are the set. They can be parallel and added together. So it is the second unknown. It is a capacitance. And the third unknown is the electron length of the connecting line. The electron length of the connecting line means the electron length from here to here. It is the electron length of the connecting line. No, now think about the case. Actually, we have a circuit topology. And we have three unknowns, 1, 2, and 3. We have 3 unknowns. And we have 3 equations. Actually, we can solve it uniquely. We can solve it uniquely. Of course, not manually, but by Mathematica or something like that. By a mathematical tool like the Mathematica. And using the mathematical tools, actually, you can solve the equation. And you can derive the ideal value of your inductance or your capacitance or the electrical length of the line. Then you substitute it back to the ADS to verify your design concept. So actually, we do not need a tuning process until we solve the equation. So actually, this is why we call it is a systematic design procedure. Actually, we do not tuning we do not need to tuning the layout until the final process, final step. Actually, we just begin with the conditions in mind. And we must, of course, choose an appropriate circuit topology, and it depends on your requirements. Maybe it is a pi network, maybe it is a little bit more complicated. And then you need some equation, and generally the equation can be derived using the ABCD matches or something. Using the ABCD matches, you can equivalent your lump element or your lump network to a uniform transmission line, and you can derive the equation. Of course, the equation will be sometimes for our Taiwan needs. I think for most of our students, they will say it's disgusting. It's disgusting because they contains a lot of variable and a lot of equations and the long equations. It is disgusting. But it is just for Taiwanese students. But I know for Indian students, you guys are very good in mathematics. You guys are very excellent in mathematics. So I think for this kind of equations, for you guys, it's just a piece of cake. All right, it's just a this. It's very simple. It just use Mathematica, and sometimes you can solve it manually, and you can derive the equations. And using the equation, you can solve uniquely for the capacitance value, for the inductance value, for the electrical length, for example, in this case. And then substitute it back into the ND, for example, ADS, Angel ADS. Actually, the Angel is outside there. They should give me some money, right? I just advertise for their software, right? Okay, of course, it is not necessary. Almost necessary to be ADS. Maybe Michael will office or some other. Just use a circuit emulator. Then you can verify your idea. It is not until the final step you convert your inductance and your capacitance and also your connecting line into real circuit blueprint. And in general, if you are designing your circuit under PCB board, there will be some discrepancy between your ideal value and your actual value. Because actually, the circuit component, for example, the parallel plate capacitance on the PCB board or the inductance on the PCB board, it is just a quasi-lump element. It still has some distributed effect. Because it is, for example, it is 1/10 of wavelength. 1/10 of wavelength also. It has some distributed effect. So generally, we need a fine-tuning process to realize the final design. But if you design it using an integrated process, which is, I will introduce you an example later on. Okay, it is designed on a process called integrated passive device process, IPD process. Actually, in general, there is a good mapping between your inductance value, value, and those realized using real physical footprint, because it is almost 100 wavelengths in terms of wavelengths, because the chip is very small. Okay, so anyway, As long as you have a topology in mind, as long as we have some features or we have some conditions, and we can solve the equations. And sometimes, for example, for these cases, this is the responses. This is responses for this line. This is for the low band, system impedance of 35 ohm, perfect match. And for the high band, 50 ohm, still perfect match. And this is the input reflection coefficient. For the high band, will match to 50 ohm. For the low band, it is almost 0.5. Why it is more 0.5? Because it is function as a quarter wavelength transformer. Think about the case, the pole 2 is loaded by a 50 ohm load. And for this transmission line, it is 35 ohm and 90 degree. So at the input pole, its input impedance is 25 ohm. So the trajectory will be stopped at 0.5 on the Smith chart. Okay, this is a demonstration of the light dual mode, the so-called dual mode, dual operational mode, thin transmission line. And for this line, this is another example. For this line, we would like the line to have 35 ohm and 90 degree in the low frequency, but become open circuit in the other frequency. And this is our typical circuit topology. Just forget about this parasitic capacitance. This parasitic capacitance is the capacitance of the inductance. Then we will have a series LC tank here. We will have a series LC tank here. And we must have the series LC tank to be, for example, let me check how many conditions we must have. At the low frequency, it is a mistyping. Okay, at the low frequency, we must have the characteristic impedance of a line equal to 35 ohm at the center frequency. And also, at the same frequency, we must have the overall electrical length equal to 90 degrees at the same time. And at the high frequency, we must have this this series LC tank resonance. So this is the third condition. The series LC tank somehow it must be resonance. And upon resonance, we must have the input admittance equal exactly to 0. Exactly equal to 0 means infinite input impedance. So think about the case. In these cases, we have 1, 2, 3, and where's the other? Because their values are somehow different from the one. Actually, we have 1, 2, 3, 4 values, 4 different values. So actually, we have 4 equations and 4 values, and of course we can solve analytically. And after we solve the equation, we can substitute it back into the ADS or a circuit emulator. And we can determine is it the response to be fine? Is it okay? Then we convert it into blueprint and then make a fine tuning. Then we can fulfill our design. But in some cases, our unknowns will be more than our equations. In that case, it will be fine. I mean, in some cases, for example, we have 5 unknowns, but we just have 3 equations or 4 equations. That will be fine because it means like we have 1 degree of freedom or 2 degrees of freedom. And in general, my experience or our experience, in general, you should select inductance first. Because inductance is in general the most lossy component in this design. And also, it is in general, it is the most distributed component. Lossy and has some distributed effect. For example, it has a step resonance frequency or something like that. So if you have some degrees of freedom, you can choose the inductance first. Then you can using your inductance to substitute it into equation. Then you have a sufficient equation, and you have a sufficient equation, you have a sufficient unknown. Then you can convert you can solve the equation and then integrate it as a full pin, a real full pin. This is another example. And you can find from the frequency responses in the low band, it is perfect match, just like a transmission line. And I did not show the phase response. If I show no, I didn't show the phase response. If you look at the phase response, you will figure out the phase response will be exactly equal to 90 degrees at the center frequency. Okay, and at the high frequency band, it is a transmission zero. But just I have mentioned about, it is not good enough to have a transmission zero at the designated band. It is not good enough. In addition, we must have its input impedance become open circuit. Okay, and this idea can be used as a feeding network of a phase array, which I will introduce later in the final of our discussion. And before that, just give you a very simple design example. It is a circuit design. But actually we use a similar circuit design in our feeding network. And this design is a dipressor design. And this dipressor design, actually we just use two building blocks. Just forget about the first one. The first one we published in 2012 in MWC. This is the first design, but we just focus on the second design. The second design is just publicated 2 months ago, also in MWC. It is an on-chip design. Actually, we just use two unit cells or two units or unit blocks. Okay, the first one is a low pass. Is a low pass or low right-handed synthesis transmission line. Right-handed synthesis, dual mode synthesis transmission line. So for this line, it must be well matched to 50 ohm in the low frequency, but become the open circuit at the high frequency. So for the other line, the situation is reversed. At the low frequency, it must be open circuit when looking into the input terminal. But it must become a transmission channel with well-matched characteristic impedance, for example, 50 ohm at a high frequency. In this sense, we use the minimum number of building blocks. We can design a dipressor. And using the jointed so-called right-handed, left-handed synthesis transmission line. And what we done here is somehow different from those deal with the metamaterial lines. In general, those guys deal with left-handed line or metamaterial line. They don't care about the response in the stop band. They just care about the, for example, fast delay or characteristic impedance in the pass band. They don't care about the response in the stop band. But we do. We do care about the stop band. In the stop band, we must create a transmission zero. In addition to the transmission zero, it must be open circuit. It must be open circuit. This is always keep in mind. At some frequency, I must make the circuit be open circuit. This is our circuit topology, and it is realized. Sorry, I will show you the layout. It is realized on the so-called IPD process, integrated passive device process. It is a process. Generally, the carrier substrate is silicon or something, high resistive silicon, and in general, it has 3 layers. The one thick metal layer and the 2 thin layers. The thin layer is for capacitance and the thick metal layer is for inductance. It's a very simple fabricated process, but it can be integrated, highly integrated with the CMOS, especially when compared to the LTCC. So many people think the IPD process will be a promising technology. Eventually, it will replace the LTCC someday in the future, especially when talking about system integration or system in package or system on package or something like that. Okay, this is the promising side of the IPD process, and we take advantage of this process. And for this part, it is a right-handed line, and this is a left-handed line. And of course, we use analytical equations to solve the problem. and the linear equations. Think about the equations. We must have our transmission line equal to a specific characteristic impedance at a certain frequency. And we have some resonance condition. The resonator must be resonant at a specific frequency. And then we must have an input impedance become infinity. I mean, the input impedance become infinity. And get together, we can solve for the unknowns. And you can find there is a good agreement between the calculated and the real number we extracted from the real grouping or real layout, because it is realized on the so-called the integrated process. Since on the integrated process, you can figure out like their values, their extracted values actually are very in good agreement with the calculated one, or only except it's a slight tuning on the first stage of the circuit. Okay, this is just to give you an example. And the most important of all, in general, our seamless transmission line, the way we develop our seamless transmission line and our circuit in general will have a very, very, very complex size. Very, very, very complex size. For example, the size of this design is less than a half of the second smallest one we can find in the literature. It is for example, in the LTCC design, it's using a high-cost LTCC, and its size is more than twice of ours. And but our responses are almost the same. It is just a circuit design example. Now we are going to the final hour of our discussion. And now we are going to the most important part of the moment. I think it's a more exciting part of our discussion. It is talking about how to integrate the feeding networks of multiple array or multiple circuit networks. Okay, the first example design here is the Rachel derivative array. I will briefly introduce you what is a Rachel derivative array. A Rachel derivative array, actually there are some group around the world which are very good in Rachel derivative array. And the first group is Professor Tatsuya Ito. Tatsuya Ito actually has done a lot of works on Rachel derivative array. And there's another group, but I'm sorry, I forgot the name. It's a long name. And then you can type the name Rachel derivative array. You can seek for some big names on Rachel derivative array. Okay, so for the Rachel derivative array, it means like if there is an array here, and if there is an incoming signal here, the Rachel derivative array will reflect the signal, automatically reflecting the signal to the direction of arrival without a prior knowledge of the direction of the arrival, without a prior knowledge of the incident angle. Okay, so it can be automatically retransmitted a signal back to the direction of arrival. And it has some applications. Just think of a case for wireless power transmission. So this is an example. This figure actually a copy from Wikipedia. Actually, it is called the so-called the solar. Use a solar cell in space to generate power, and using microwave energy to transmit the power, wireless power, to transmit the power to the ground site. So actually, it is maybe it is a way that in the future we can gather some power from space and to the ground site. And you can understand this is a solar cell or the satellite in space, right? It is a satellite in space, and they are also solar cells. Okay, they collect the power, and then they transfer into the so-called I power, and definitely the I power will be very high. For example, it will be kilowatt or maybe a megawatt or something. Okay, then they radiate the power with a very narrow beam, and to the ground side with a rectangle. Rectangle means rectified cross antenna. And then we can convert the microwave signal or microwave energy into DC energy and to our electrical network or something else. But think about the case. What would be the case if there is a misalignment between your satellite and your rectangle? Misalignment. I mean, if the orientation of your satellite and your ground side somehow the misalignment, then you can get the illumination, right? Your rectangle will not get the illumination. And what is the other problem is it has a very high power. It is high power, and it is offset somehow, offset or something, and it will illuminate to somewhere else. And if there is an animal, I don't know what will be the result of the animal, be crooked or be somehow else. So we need a pilot signal. We need a pilot signal to instantaneously to echo to the beam of direction of arrival. Okay, to echo to the beam of direction of arrival. This is the application of a retrodirected array. Once you have illuminated the rectangle, then we can use a very small, a very tiny retrodirected array, and it can automatically generate the pilot signal, and the pilot signal can retransmit it back to your satellite, and your satellite will monitor your pilot signal continuously, and once it finds it loses the pilot signal. It means like there is some misalignment between the satellite and the ground side. Then the satellite somehow it knows like first of all it maybe must desist stop the transmission, and then it must change its orientation until it can receive the pilot signal or something like that. It is an application of a retrodirected array. And of course, the retrodirected array can do some radio frequency identification because it is just a similar idea like a radio RFID system. If you can add some modulation, and actually we did add some modulation now. If you can add some modulation in your retrodirected circuit, then actually you can make the retrodirected array similar to an active tag. You can transpond your work information, like the temperature. Then just think about the sensor node. You can transmit back your temperature or your humidity or some other information to the direction of arrival. Okay, this is for the RFID or surveillance system or object tracking in the same way. So actually, for the retrodirected array, there are some promising applications. Some promising, possibly maybe not in daily life, but in military or in satellite communication at least. Okay, and there are some conventional ways to realize a retrodirected array. The first one is named after its inventor. I think it's about 1970 or something. 1970 or 1960 something. Okay, it's called Van Alta array. The Van Alta array, actually just think about how to make the incident signal. How to make the retransmitted signal to the direction of the incident signal. Actually, we have a very important phase condition. This phase condition means you must have the phase difference between adjacent antenna elements be reversed. That is, the receive phase of the first antenna element should be transmitted to the last element. And the phase you received at the second element should be transmitted to the second last element. And with this manner, you can reverse your phase. And in this case, actually, the incident signal will retransmit it back to the same direction of arrival. And actually, there is another term called the refractory array. The refractory array means that your retransmitted signal will in the speculative direction of the incident of arrival. It is another story, and we are just developing the refractory array somehow, and we're talking about in the future. Okay, we're just focus on the retrograde array, and this is the Banach array. The Banach array. Its idea is very simple. The phase you receive at the first element will transmit it to the last element. The phase you receive at the second element will transmit it to the second last element. And keep in mind, these connecting lines should be equal to multiple of guiding wavelengths. A multiple integer of a guiding wavelength should be equal to a multiple integer of a guiding wavelength. Like this connecting lines has not any effect. You just receive the signal and send the signal to the antenna pairs. And of course, if you add an amplifier here, you can amplify the signal. You can amplify the signal. Okay? If you put the amplifier here, put the amplifier here, and put the amplifier here, then you can amplify the signal when retransmitted. This is the so-called Banach array. The second type of the retroderivative array, we call it the phase conjugating array. This is the most Professor Ito involved, phase conjugating array. And actually, the best idea is very simple. It's just a so-called heterogeneous structure. Just think about we have a common local oscillator. And we have a mixer here. We have a series mixer here. Generally speaking, there was some mutual locking or something between the mixers. And think about there is an incident wave here. And in general, the LO frequency will be twice RF frequency, exactly twice the RF frequency. So what will be the result after you mixing them? You have an LO signal. You have an RF signal, and the LO signal is twice of the frequency of the RF signal. Then, after mixing, you have at least two components, right? The first component is the sum of them, get rid of it. It is at a high frequency. And the difference of them, once again, it is at a RF frequency. And the most important of all, it is the difference of them. It is a difference of length, means like you have your phase reversed because of the subtraction. Because of the subtraction, your phase, incident phase, is reversed. So in that pattern, in that sense, actually the incident signal will retransmit it to the direction of arrival. This is the second type of the retroderivative array. And traditionally, just two types, the Banach array and the phase conjugating array, two types of array. And recently, we noticed like there is another type. Original name of this type of retroderivative array is called the linear retroderivative array in light paper. And light paper is also published in 2008 in AP transaction on antenna propagation. Okay, and for this array, actually it is invented by one of my junior and with his advisor in NTU, and his advisor is Professor Chu, Daxiong Chu. Okay, it's also a Taiwanese. And actually, for this kind of retroderivative array, it uses reflection law. Okay, so my personally referred it to as, I named it as a reflection type retroderivative array. I think it's a proper term because it uses reflection law. And actually, it uses a lot of crossover and the delay lines or something. It is actually similar to a Banach array. But in this way, he deals with this problem. He used crossover, and then he used branch line copper to change the signal, to switch the signal from the first terminal to the last terminal. and from the second terminal to the second last terminal, and so on. So this is the second type, and third type of a retroderivative array. And my question is, I actually, in 2008, this is my first time I read this paper. Hey, I found it, hey, this is interesting. And I just asked my student, hey, collect as many as literature on retroderivative array as possible. So they collect some array, design regarding the Venn array. They collect some designs on the phase conjugating array and the retroderivative array. And then I asked my student, what else I can do? What else we can do? They just have a very good design on the Venn array, very good design on the phase conjugating array, very good design on we can abbreviate it as a PCA, okay? And they have a very good design on the reflection type array. What else we can do? And then later on, I think about how about we have a dual band design or dual mode design. I mean, we combine the feeding network over two. If it's possible, we combine a Venn array with a phase conjugating array, for example. Or we combine the feeding network of a Venn array with a reflection type array. Is it possible or not? This is the best idea in mind. And I don't want to use any switch. I don't want to use any pin diodes because they are noisy. I don't want to incorporate this diode or switches in my feeding network. So what else I can do? And just I have mentioned to you, I have talked about someday I just taking a shower. Generally, taking a shower is a good time for your life because you can do nothing, just stand there, right? You can do nothing, just stand there and take a shower, and you can think. And the most important of all, you can think. Your mind, you can think. Of course, somebody says when you sleep, you can think. You can come up with some idea. Just like you know the real famous story about the chemistry structure of the benzene. I mean the C6H6, right? And I heard about the story. Someday when he sleeping, he had a dream. He saw a snake, right? Snake, and bite his warm tail. And he come up his mind. For the C6H6, it should be somehow like a ring. The chemistry architecture like a ring or something like that. Of course, sleep is a good way, but for me, sleep just sleep. I cannot do something innovative on my research, but taking a shower does work. And when I take a shower, and I can do nothing but thinking about research or something else. Hey, it comes up to my idea. Hey, our synthesis transmission line. What about our dual case? And then we can combine together. Then we can have a dual mode array. We can have a dual mode array. And the first dual mode array, actually, it is published in TMTT. I submitted in TMTT, not TAP, because most of the part we're talking about the feeding network is a circuit part, not the antenna part. But actually, the whole system is an antenna, is a phase array, right? It is a phase array. And we actually, this is the first, we call it the heterogeneous integration of multiple phase array system. And actually, in this system, we integrated the feeding networks of a Venn array and a reflection type array. Of course, we actually also do successfully with a phase conjugating array and a Venn array, but we do not publish it in the literature because in the paper, in the conference or in the journal, because they are routine, they are almost the same. They are all the principle almost the same. Just now, we just take a look at the Venn array and the reflection type array. This is the architecture of the Venn array and the reflection type array. It looks like quite complicated, right? But actually, the principles are quite easy. We just need two core building blocks. The two building blocks, we call it, it is a dual mode quadrature hybrid, means branch line coupling. It's a dual mode branch line coupling. Be careful about the mode, dual mode means. I will explain the dual mode later, okay, in the next slide. and the other is the dual mode crossover. Now, what is the dual mode building blocks? The dual mode branch line cover means that in this design, in the low band, it is just a branch line cover. It is just a branch line cover. But in the high band, the shunt passes should be open circuit. Should be open circuit. We cannot allow any shunt passes in this design. The signal has no way but just flow from pole 1 to pole 2, and to flows from pole 4 to pole 3. They just appear like looks like a pair of isolated transmission line. Just like look like an isolated transmission, a pair of isolated transmission line in the high band. Similarly, for the dual mode crossover in the low band, it is just like a traditional crossover, planar crossover, using a combination of two branch line cover. But in the high band, it will become, once again, a pair of isolated transmission line. Okay? Have this in mind. If you substituted the ideal into this array, what will be happen? Just think about, in the low band, all these function blocks will function ideally as a branch line coupler or as a crossover. So it is just the topology of a reflection type ratio-directed array. And think about the case, we have a open circuit stub here, and this open circuit stub will become a reflection load, a short circuit reflection load at this point. So actually, this connection line will be no longer exist in the low band because this point will be short circuit. So for this design, actually, it is just like a reflection type ratio-directed array. But in high band, just think about the case. All the shunt passes, all the coupling passes cannot exist. So what you see here is a direct connection from pole 1 through the connecting line and to pole 2n. And from pole 2, because there is no coupling passes, right? So the pole 2 is connected directly to the second last pole, and vice versa. So in these cases, in these senses, actually, we combine the ratio-directed array and the Violetta array as a whole, using a single topology, single feeding network. We don't introduce any active switches. We don't introduce any active MEMS or diodes or something. We just use a concept of single-stage transmission line and the multi-operational mode single-stage transmission line, and make the single-stage transmission line be open circuit, especially for this shunt element, be open circuit at a single frequency. Then this part will become invisible. So you can take a look. This is the response of this crossover, In the low band, it is ideally a crossover. It is a signal from pole 1 to pole 3 and pole 2 to pole 4. It's crossover. Okay? But in high band, this is our first design. So the response somehow it is not really very good. But it's okay, still okay. And in the high band, just think about this curve. This is S21. It means that your signal has no choice but flow from pole 1 to pole 2. And you cannot propagate from pole 1 to pole 3 or to pole 4 because they are all isolated. Yeah, this is the basic idea behind. And we use a 4-element array as a design example. This is a 4-element array. And actually, it is done just by one of my master students in 2 years. So I'm very appreciate him because it is a large system, and it is the first system we developed. So it is a very complicated system, but actually it is In my point of view, it is a little bit quite beautiful, right? It is quite beautiful. It is just a beautiful topology, and there are dual mode crossover here, and dual mode bridge line here, and they have some connecting line and matching unit. In the low band, it is a reflection type ratio derivative array, and in the high band, it will be a Van Matter array or something like that. It is a single flow. It is a single flow from pole 1 to 1, 2, 3, 4, and the 5, 6, 7, 8 is also 5, 6, 7, 8. They are the same. Just for simply clear expression purpose. Okay, so in this case, actually we do the experiments. Okay, this is the experiment in the low band. We have illuminating antenna. Okay, illuminating antenna, and I must have a dual mode ratio derivative array here. And we using a receiving antenna and retransmitted, and using a measuring antenna to measure the retransmitted pattern. The retransmitted pattern, sometimes we call it the backscatter pattern. And this is the result. This is the result. In addition, regardless, despite of these reports, actually there is a good agreement between the simulated calculation and measure the results. And the reports is because it is our first time to design such an array. So in this design, actually we do not calibrate the cluster from the anechoic chamber. We do not do the calibration. So there's some kind of report, Yeah, we do find notice some problem, but this problem actually you can no longer be observe such kind of problem in our later on works. And you know, one of my colleagues, his wife, someday he saw this paper and say, hey, he told to his she told to her husband, hey, your colleague is excellent. Why? My colleague asked her, why he's excellent? Because his work is beautiful. It's like a flower or something. Oh my God! Is it because like we don't properly calibrate the cluster signal, and then somebody else not in this field say it is beautiful. I don't know how to say. Is it admire or it is I don't know. Is it just a joke? But is it true? Is it true? So it is a true story. Anyway, it is our first work. It's our first work. We successfully combined, and I believe it is the first work to combine the feeding network of two ratio derivative array as a whole. And it is a long story. It is a long paper. I think it's 14 pages. 14 pages means it cost me $1,600 to pay the pay charge, or is a lot of it is a large amount of money, because the MTT has a very limited page number. It's just 6 paper, and it exceeds the 6 paper, then per paper $200. Oh, it's very expensive. Anyway, it is a long paper, and we got a very short comment. When the review, it is just a minor revision, and it is a short comment. And the reviewer said that you did a very excellent work. It makes me the way you think this. I still remember his comment. The way you think this is the feeding networks is a surprise to me. It's a surprise to me, and it made me think like the ratio derivative array still has something to work on with. Okay, it makes me very happy, because it is our first work, and you know the measurement result is not very good, but actually we got some good responses, and we got some good feedback from the academic field. So this is our first design, and the second design we want to move forward. So what would be the case if we would like to integrate a beam switching array? I mean, using butter matches and a reflection type ratio derivative array, for example, as a whole. Is it possible? Is it possible? And just think about a scenario. Just think about a scenario. If we have a smart AP here, smart AP access point, I mean smart access point. And this access point can do communication using a antenna in bottom matches mode, okay? In do some communication. And do positioning. Why we can do positioning? Because bottom matches is a beam switching network. So at some certain extent, you can do some positioning capability. And we can do some interrogation and backscattering or something like that. It means like it is an RFID system. And we can do some wireless power transmission using the Van Alta array. If the Van Alta array we add a bidirectional or even unidirectional amplifier, it could become a unit for wireless power transmission. It has been demonstrated in the paper. In some paper, I will show you the paper later on. It's not by me, it's by somebody else. And it demonstrates like the Van Alta array together with a bidirectional amplifier or something like that. And it could realize the so-called wireless power transmission or wireless charging using the far field approach, not near field approach, not magnetic coupling, not magnetic resonant coupling, but far field approach. Okay, so how to deal with it? Just think about the topology. We just limited on 4-element array. Now, just get a close look at the bottom matches. Okay, this is the topology of a 4x4 bottom matches. A very typical design, right? You have a 2 crossover. You have a 4 branch line copper. You have a 45-degree delay line here. Okay, fine, it's okay. And it is the radial directed array. I mean, reflection type radial directed array. Fine. You have a quadrilateral hybrid here. You have a crossover here. And you must be open circuit. Of course, short circuit is fine. Okay, open circuit at the end of the input port. So just think about the topology of the two designs. They are very similar. They are very similar. The only difference is in the bottom matches, they are input port at port 1 to port 4. But in the reflection type radial directed array, they are open circuit. And the second is there is additional dual mode. There is additional crossover in front of the bottom matches. So what would be the case if we would like to combine the feeding network of the two as a whole? Yeah, it's simple. Just let's start with a 4x4 bottom matches. It is a bottom matches. First of all, is it possible we replace these lines with dual mode delay lines? The dual mode delay lines means like it is a transmission line in the low band. It is 50 ohm line. So for the bottom matches, okay, it is just an input port. It is just an input port. And for the upper band, I mean for the upper band, for the other band, they become the open circuit at the input port. So they become the reflection load for the reflection type array, radial directed array RDA. Okay, yeah, okay, it's fine. And the second part is, how about we introduce a dual mode crossover here? A dual mode crossover here. In the low band, here. In the low band, it is a crossover. It is a crossover. But in the high band, it becomes a pair of isolated transmission line. Okay? It's quite simple. But using just two key components, the dual mode delay line and the dual mode crossover. Of course, I know the dual mode, the term here is somehow some person will argue with me because actually you are not a dual mode crossover because it is a crossover only in one bit. But I couldn't find any better term of it. So I just use the term dual mode crossover. Okay? Anyway, in the low band, it is a conventional crossover. But in the high band, it becomes a pair of isolated transmission lines. And in these cases, actually just two dual mode new components, and we can combine, we can get their I mean their phase arrays get together. The infinity network of the two arrays get together. And the story I would like to ask you is integration of the bottom matches and the reflection array readily achieved, easy achieved, just replace the two. Not that easy, because we are talking about the phase array. We are talking about phase array. When we're talking about phase array, we are care about the phase. We care about the phase. And this crossover in the alphabet, it has additional phase delay. And this phase delay should be taken into account. So actually, in addition to replace your input port as the dual mode delay line, in addition to replace the crossover with the dual mode crossover, actually you need a phase compensation. The phase compensation actually can be achieved by simply just several segments of transmission line. The objective is very simple. In the low band, it must be function as a bottom matches. So we can get some equation. We must have the phase delay of this delay line equal to the phase delay of this delay line or something, or they have a specific phase difference. Just follow the conventional bottom matches. Okay, and in the high band, the phase delay due to this delay line and the phase delay due to this delay line in addition to the additional delay of this crossover. The summarize of them should be equal to each other in addition to a multiple integer of 2 pi. So we need a phase compensation. And this phase compensation, actually, we can have some equations. And using these equations, we can solve for the electron length, require the electron length for this compensating line. For this compensating line, we can solve for the equation. And after we solve for the equations, actually, we can derive for the unknowns, for example, theta x, theta y, or theta z, or something else. And after that, we finish our design. Just think about it. We have some topologies. And we found their similarity. And then we replace the core components with dual mode ones. And then we add some phase compensation lines. And then we put it together. Then we figure out like we complete the design. And this is the whole circuit to perform the measurement. This is the dual mode circuit, feeding circuit. I just give you a quick illustration of the circuit. Where is it? I didn't show you the circuit. Why? Here. Yeah, this is a dual mode feeding circuit. Okay, these are just a dual band crossover because they don't function as a dual mode one. Okay, and this is the dual mode crossover. In the low band, it is a crossover. In the high band, it is a pairover transmission line. And these are the dual mode delay line. It is just like a conventional bottom matches. And of course, if you are interested in it, you can transfer it into an IC design. Transfer into, for example, in the IPD, you can of course transfer into an IPD design. And you can make it as compact as possible because it is just a feeding network. Okay? And we just develop a 4-element array as an example. And let me show you some of the responses. Okay, this is a whole system we used to measure the results. We have a circulator here. The circulator is separated between the incident signal and the retransmitted signal. And also, in the beam switch mode, this part should be inactive, only this part will be active. Okay, and this is the part for the input signal in the beam switch mode. And in the ratio directed mode, because the open circuit, this part will become the inactive. Okay, so these are some typical results. This is a component, the results of a component. This is a dual mode line, or dual mode crossover. In the low band, it is a crossover, and in the high band, it is a delay line. In the normal line, a pair of isolated line. And for this case, it is the second version of our design. You can figure out the response is much more better than the first one. Our isolation could be better than 15 dB, and our return loss could be or the information could be better than 20 dB or something. So yeah, it is pretty good, and we integrate it as a whole, and add some antenna. For this antenna, it is just a typical quasi-Yagi antenna. It is just a typical planar quasi-Yagi antenna, and a good front-to-back ratio and a high gain or something else. Of course, we need a good front-to-back ratio. Otherwise, the illuminating antenna will interfere with the measuring antenna or something else. And we do the measurement. The first one is the response in the low band, and it is perfect, just like a conventional bottom matches. Just like a conventional bottom matches, we can switch the bit. If you add some fast shifter, actually we can steal the bit. Of course, we can steal the bit. Of course, okay. And in the high band, this is the fast response. I will skip it due to the time limit. This is the response in the high band. You can see this time it's no longer be a flower. Okay, it no longer be a flower. It is a much better agreement, improved agreement between the simulated and the calculated result, because we calibrated out the clutter from the anechoic chamber. So the results will be pretty much good. Okay, this is the second design of our work. In this design, actually we combined the radio-directed array and the beam switch array as a whole. And my student actually moved forward. My student tell me, hey, professor, hey, sir, is it possible we design a tri-mode based array? Is it possible we design a beam switching Banata base conjugating array? I think, what is the purpose? He said, for the beam switching, of course, we can have a communication channel. We can have some positioning functionality. Okay, and for the Banata array, we can have the wireless power transmission. And for the PC array, we can of course add some information, our own information through the local oscillator or low variation data that we can function as a RFID system or semi-active tag or something. And in his mind, he'd like, once again we see this picture, in his mind, he would like to have such kind of integrated array eventually will be integrated in the IC circuit, and it will be a part of an access point. And the access point will be smart. It can communicate with something, with others. It can position it to some extent. And it can do wireless power transmission. And also, it can reflect back some warp signals of its warp. For example, think about the access point that has a sensor, is also a sensor node. It has some measure the temperature, humidity, or something else. And it can retransmit this kind of information using an RFID signal, or using RFID mode, I mean the PCA mode, to the interrogator or something else. Yeah, this is our viewpoint and our objective. Okay, and this is a detailed illustration. This is in the low band, it is a beam switching array, and this is in the mid band, it is a Banata array. We just connected into pairs, and this is the design in the high band. It is a PCA array, base conjugating array. Hey, it is quite complicated because we must have a single topology, but have the triple functionality, and it is quite difficult So actually, we need some unique circuit component. And this circuit component actually will be quite different from the previous ones ever published in the literature. And this is the core component in this tri-mode array. The core component, we call it the 3-channel selector. So let me just focus on the 3-channel selector. Actually, this 3-channel selector, because think about it, it is a complicated structure. Very complicated structure. If I design a system, of course we have completed design a system. If I write a paper regarding the whole system, this paper will be 20 or something pages. Which means that it will cost me maybe 10, or not 10,000, or maybe anyway, it will be cost me a lot. So I asked my student, let's separate into 2 parts. The first part, let us just talking about the core component, and the second part, we're talking about the whole network, And for the first part, it has been published last year, October. It is called the 3-channel selector. And the second part, it is actually under minor revision now, and hopefully I think it will be accepted in a week or so. It is just be under revision, and there's no other major concern about it. So I could share this work with you. It is uncomplicated, and just take a close look at it. It is actually still follow the topology of a bottom matrix. It's still the topology of a bottom matrix. Okay, this is the branch line cover, and this is crossover, branch line cover, crossover, and almost we need a diplacer here. Why we need a diplacer here? Because for the bottom matrix mode, bin switch mode, the input signal is from port 1, 2, 3, and 4. But for the PCA mode, the local oscillator, the signal from the local oscillator will coming from the 1 prong, 2 prong, 3 prong, and the 4 prong. So they are different. So we need a diplacer here. And we need some spatial design of the coupler and also the so-called crossover. It is a crossover, but this crossover is so unique, and we do need to find a way to describe them. And I term it as a 3-channel selector. There is a story I will tell you shortly. And just think about the signal flow. In the no-band, if your input signal is at port 1, it will even spread it to port 5, 6, 7, 8, and with a pre-described phase difference. So it's a bin switching array. And in the mid-band, actually all serial passes will be forbidden. So the signal can only propagate it from here to here, to here, to here, and to antenna 8. The signal incident illuminated at port 6 or antenna X port 6 will only propagate here to here and to antenna 7. It means like in the mid-band, the serial passes should be invisible to the whole feeding network. Once again, dual mode, no, not dual mode, tri-mode. Why tri-mode? Because in a high band, all shunt passes will become invisible. So if there's an incident signal from port 5, it will come along to port 1 prong and to the mixer, to the local oscillator, and then refreshing back to the antenna port 5. Okay, this is the operation principle in the high band. So in the high band, it is a phase conjugating array. Okay, for example, you can for radio frequency identification or surveillance or object tracking or something else, just like Professor Ito has done a lot in the past 10 years or past 1 or 2 decades. And for the mid-band, it's just a Banach array. because all the serious passes are forbidden. And for this mode, if there is a bidirectional amplifier, we haven't yet added bidirectional amplifier, but it's quite routine. If you have a bidirectional amplifier in the passes, it can relay the power and it can amplify the power. Just think about the case if there is any incident signal here, and through the binocular array, you amplify the signal and you retransmit it back. And you can charge, for example, some devices. You can charge some devices through the far field way, This is our deal. Okay, so we are now turn our attention to the core building block, which is we so-called the 3-channel selector. It is just a crossover. Okay, in the low band, it is just a crossover. The signal is from port 1 to port 3, port 2 to port 4. It is just a crossover. But in the mid-band, the stereo passes should be invisible, open circuit. So it once again becomes a pair of isolated lines. And in the high band, it once again becomes alternative isolated transmission line. Instead of a parallel, now instead of in the shunt passes, now it is become serial passes. So difference between the mid-band and high-band is this. So what is the term? If you have a microwave component, its response is like this. Just ask yourself, if you would like to have a term, if you want to name a microwave component and its response is somehow like this, no one else in the past do something similar to this one. So actually, it confuses us a lot. In the original, we think it is more like a triplacer. It's more like a triplacer because we select the channel. But it is not a triplacer. Because for a triplacer, we have a common input. And the common input will propagate into port 2 at one frequency, port 3 to another frequency, and port 4 to a third frequency. But in these cases, each port can be the common input. It is not a triplacer. It is not a typical conventional microwave building block. So it confuses a lot when we would like to prepare and we like to submit a paper. The most important of all, what will be the title of this paper? I don't know. What will be the title of this paper? I don't know. I don't know how to call this. It's a dual mode crossover? No, I don't like this name. It is a triplacer? No, it is not a good name. It confuses us a lot. So someday, I just asked my PhD student. He has received his PhD degree last year. I just asked my PhD student, okay, let's go to dinner. Let's go to dinner together and discuss this and just have dinner. Actually, I don't know what I'm eating because I'm just thinking. And thinking, and it come up to my mind. So the other activity, important activity in your life, daily life, is eating. Okay, I hear the noise of the dishes, right? Okay, everybody got hungry, and we could discuss during the dinner. Okay, maybe we could come up with some new idea. And then during the dinner, it come up to our mind, come up to my mind. How about we call it 3-channel selector? Because we select a channel. I asked my student to search, to perform a literature survey. Is there anybody called channel selector or something else? And after the dinner, my student tell me, yeah, somebody called the channel selector, but they are in the digital form. They are just in the digital part. No one in the microwave frequency or microwave circuit called some components as a channel selector. But I think, anyway, I don't care about it. It is a channel selector. I say it is a channel selector. It is a 3-channel selector. Just submit a paper as a channel selector. No. Then we submitted to the MTT. And at that time, the editing chief is George Puncture. Okay? And 4 months later, we got the responses. And I'm very happy to see George Ponchik, the editing chip, leave a word. This is one of the most interesting work I have read for a while. One of the most interesting work I have read for. Oh, I'm so proud of my student because it is his idea. This is his idea. He just come up with dual mode line to tri-mode lines. And I will introduce in detail how to realize this 3-channel select. Just think about the condition we would like to have. In the low band, it should be functioning as a traditional crossover. So we have 50 ohm line, we have 35 ohm, we have 50 ohm line, we have 35 ohm line. And we must have our phase delay equal to 90 degrees, right? And in the mid band, there is an open circuit condition in the series package. And in the high band, there is an open circuit condition in the shunt passage. So actually, we must take care of the tri-band at the same time. So we need the so-called tri-mode building block or tri-mode density transmission line. Tri-mode density transmission line. And this is a more clear illustration. Channel 1, input signal, output signal. Of course, input signal, if it is here, it will come out here. Okay. And for the channel 2, input signal here, output signal, and input signal here, output signal here. Okay. And for the channel 3, input signal and input signal. And think about the case for this line. In the low band, it must be a 35 ohm line and with 90 degree phase delay. But in the mid band, it must be open circuit. And in the high band, it must be 50 ohm. The characteristic impedance must be 50 ohm. So actually, we have 3 different kinds of conditions. And we actually do need to try a lot of networks. Of course, just what I have mentioned about in the previous hour. Actually, we always start from certain topology. In these cases, we use this simple, actually just a series tank and with inductance, with capacitance, and with an additional transmission line. Now, think about how many conditions we have. We have 1 unknown, 2 unknown, 3 unknown, 4 unknown, 5 unknown, 6 unknown. We have 6 unknown, right? We have 6 unknown. And how many conditions? We have 6 unknown. How many conditions we have? The first one, 35 ohm at low frequency. The second one, 90 degree at low frequency. And the third one, there is a transmission 0 due to the LC tank at the mid frequency. And don't ask me why there are 2 LC tanks. It is just my student said I want it to be symmetry. Okay, so there are 2 LC tanks. There's no particular reason. Okay, so there is a transmission 0 at the mid band frequency. And at this frequency, when you look into either side of the network, it should be open circuit. Okay, it should be open circuit. And the fifth one is at the high frequency. The whole circuit should be equal to 50 ohm. And then there's an additional requirement. We simply let the characteristic impedance of this delay line equal to 50 ohm. Now we have 6 unknown and the 6 equations. We can uniquely solve using Mathematica. Indeed, we solved it using Mathematica, and we substitute back into a circuit emulator. Check its response. The response was somehow like this. There are 3 curves here. Modeled, using this non-modeled, and the full-way simulated, and the measurement. You can find in the low band, it is a 35 ohm, 90 degree delay. And in the mid band, it is open circuit. And in the high band, it is 50 ohm. It is 50 ohm. And you know, this is a co-building block of our whole feeding network, right? And actually, we submitted this to the IMS, International Microwave Symposium. Okay, International Microwave Symposium. I think it's this year, last year, microwave IMAX last year. But actually, we just call it a tri-mode synthesis transmission line. And we submit it to IMAX. And think about it, it gets rejected. It gets rejected. It gets rejected. Why? I think it is understandable because IMAX just has 3 pages. So we just illustrate, we do a tri-mode synthesis line. If I am the reviewer, I will answer a question, what the hell it is? What the hell is it? I don't know what is the application. Because in a short conference paper, we just illustrate the very initial idea of the synthesis line. Nobody has idea what is the application of this line. So it gets rejected. I accept the decision. I understand that. But anyway, we rearrange the whole circuit and we submit it to the journal paper. It gets accepted. This is another block. It's another block. And for this block, the condition is somehow different. This block is being used in this part. Okay. In the low band, it should be 50 ohm, 90 degree. In the mid band, it should keep the 50 ohm. And in the high band, it must become open circuit. So, of course, once again, we have 6 unknown. And we have 6 equations. We can solve together. And we can get our results. In the mid band, in the low band, they are all 50 ohm. And in the high band, it becomes open circuit. And the phase delay at the low band is exactly 90 degrees. Exact 90 degrees. Okay, so this is the way we think this is the so-called triphase. Just forget about the second line and the third line. The third line is actually just a parallel connection of the second line. It is just a 50 ohm become 25 ohm. It is very simple. So this is the core building block, which we call it a 3-channel selector. In the low band, pole 1 to pole 3. In the mid band, pole 1 to pole 4. And in the high band, pole 1 to pole 2. And we have a good isolation between them. This is the low band at 0.7 gigahertz. And this is mid band at 1.8 gigahertz. And this is high band, we have at 3.5 gigahertz. And actually, you will ask me a question, how about the frequency ratio between them? I forgot about the exact number, but actually the flexibility between the frequency band, actually, they are quite flexible between the frequency ratio between the bands. Actually, you can check out our paper. I think it's 1 to, I forgot the detailed numbers, but actually we do have some flexibility on selecting the ratio between the bands. So it is not fixed. It has to be 0.9, 0.7, and 1.8, and 3.5. It hasn't to be. It's just for as an example. It hasn't to be fixed at such a kind of ratio. Actually, the ratio is quite flexible. Okay, and we combine it, and of course we compare this 3-channel selector with conventional state-of-the-art triphase. In addition to its functionality, actually it has the smallest size. It has the smallest size because we use the slow wave approach to reduce the size. So it has the smallest size. Meanwhile, it has additional functionality in addition to a triphase. Okay, this is an essential part, the 3-channel selector. And then we also need a phase compensation because of the time. And this is because of the time. And this phase compensation is quite similar to the one I introduced you in the dual mode design. So I just skip the part. It is very simple. In the bottom matrix, you must keep the phase delay as a bottom matrix. In the mid band, you must keep the phase of this part equal to the difference between multiple of 2 pi. Okay, and in the high band, the whole network. Okay, the whole network. The phase difference between the 2 paths should be once again a multiple integer of 2 pi. as the PC array. So this is the button matches mode, and this is the Van Arco, and this is the educative. For the one, of course, it's a large, it's very large. It's a very large PCB board. But of course, if you convert it into, for example, into IBD design, it could be still could be inductance and the capacitance and transmission line to realize such a tri-mode feeding network. And think about, we have 3 channel selectors here. We have tri-mode copper here. The tri-mode copper is similar. It's a copper in the low band, and it has a transmission path in the mid band, and it has another transmission path in the high band. And we have a dipressor here, and we combine it together and to measure the results in the low band. Perfect, almost perfect. It is a bottom matches. It is a beam switching antenna. And in the mid band, of course, we did not incorporate with the bidirectional amplifier, but it is still a Van Arco array with ratio directive. The incident signal is here, and the reflected retransmitted pattern is also in the same direction. Okay, and in the high band, once again, it is a ratio directive array. And if we have some modulated signal in the L, for example, we have a data rate of 2 megabits per second. I didn't do the results, but we do have the results. For example, if we have a LO, and the LO, for example, has a low data rate, for example, 2 megabits per second or something, then you can retransmit the signal. The illuminating signal is a continuous wave, but you can add your own information from the local oscillator. Then you can retransmit your own data to the interrogator. It is a principle of RFID system, right? So in this way, you can use the high band to become a semi-active RFID tag or something like that. This is the whole network of our discussion, of my presentation or our discussion. So in conclusion, we have a complete introduction to the synthesis transmission line. Its design concept, its multiple operation, and the most important mode. For each kind of circuit, we have formulation, and we have some applications, and we have some integrated array, and actually we have moving some forward. I'm not sure here. And actually, if we use left-handed dual mode synthesis transmission line, we can switch the operation. In the low band, it is a ratio directive array, and in the high band, it becomes a beam switching array. And we can develop a ratio refractor array or something like that. Not a ratio refractor, refractor directive array or something like that. It is the way I think this is the transmission line, and the way. The basic philosophy. Basic philosophy in mind for me is I want to do something different from the others. I want to do something different, uniqueness. So this is why I choose this topic, and fortunately enough, we do have some good results. And hopefully you can find these results maybe 2 years later in a book regarding the synthesis transmission line with phase array application. And we will add additional examples. And I will have an additional chapter talking about the 2-dimensional routing of synthesis transmission line also. Okay? And let me use 5 more minutes to introduce our research center. A little bit. Okay, this is my university. My university. Our university is of course NTUST, National Taiwan University of Science and Technology. Okay, we have a nickname. We call it the Taiwan Tech because we are the toughest vocational oriented university in Taiwan. Okay, so actually, the overall rank, I think in the overall rank in the Asia region, our university is about 50, ranked 50, and the NTU without the ST, NTU without the ST. I mean, a university without science and technology. I'm just kidding. Okay, I graduated from NTU. NTU is ranked about 20 or something. Okay, in Asia, in Asia region. And actually, this is our research center. Actually, we got a lot of antenna measurement systems. We have actually 1, 2, 3, 4, 5 anechoic chambers. Okay, and 3D far field, 2D far field anechoic chamber. We have 1 3D near field anechoic chamber. And we have a 3D near field anechoic chamber. We have an EMC chamber. We have a planar near field for high gain, for example, base station antenna or something like that. So we have a planar near field anechoic chamber, and we will have a millimeter wave channel in this year. Millimeter wave from, I think it's from 50 gigahertz to 100 gigahertz also. And this is our equipment. And of course, we have a strong support from our government. You know, we have a center called the Chip Implementation Center. And the Chip Implementation Center is an organization of the government. And actually, we can just deliver our chip design, our layout to the chip, and we call it CIC, Chip Implementation Center. And then we'll get reviewed. If it passed, then we'll get a grant to tape out our IC. In this sense, actually, we just paid about several $1,000 or several $10,000 NT dollars, 10,000 NT dollars, which is equivalent to maybe just $1,000 US to have our chip. It's very cheap and it's work very well. It's a good business model in Taiwan to link the academic and industry, especially TSMC, together. Okay, this is a good way to work with it, and we have some probe station in our university, and also we can do the performance in do the measurement in the CIC. Okay, it's a way that we integrated our research energy get together. Okay, and this is some facility and some picture of our anechoic chamber and our equipment. And the last but not the least, our Taiwan will host. No, thank you for your attention. Our Taiwan will host this year ISAP. Okay, at Kaohsiung, Taiwan. Okay, this is in the southern part of Taiwan. This where is? Oh no, there's no Taiwan. Taiwan is a small island, right? And Kaohsiung is in the small southern part of Taiwan. And during the winter, even actually there's no winter at Kaohsiung. It's a very comfortable in the winter. Okay, just like you in the winter is a dry season, right? In the dry season for you, and in the summer it is will be the rainy season, right? And in Kaohsiung, it is the same case. In Taipei, although Taiwan is very small, it is just 300 kilometers from Taipei to Kaohsiung, but the weather is completely different. Generally speaking, in Taipei, for example, it is will be, for example, 15 degrees. 15 degrees, 15 degrees is okay, but actually think about 15 degrees, but raining with 100% humidity. It feels like 5 degrees. It feels like 5 degrees. It's very cold. But in Kaohsiung, maybe it is 25 degrees with sunny day, always sunny day. So actually, it's a good place to visit, and you are very welcome to submit the paper to the ISAP 2014. And the preliminary submission deadline is July 4th. But I'm sure we will get some extension, maybe 2 weeks or 3 weeks. So you still have plenty of time to get your paper prepared and submitted. And the general chair is Kino Wong, who I believe he's a well-famous guy, yeah, in the antenna community because he's a guy with I think his publication is more than 500 or something, 500 technical papers regarding all small antennas and mobile antennas or something. Yeah, and I'm the TPC co-chair, so I have the responsibility to advertise our conference. And you are very welcome. And the website. Oh, sorry, I typed multiple HTTP. Just one HTTP here. Okay, so you are very welcome to join us. And please do not hesitate to email me if you have any problem to submit a paper. And if you have the time, opportunity to visit Taiwan, please do not hesitate to email me. I will try my best to host you in Taiwan, to welcome you in Taiwan. And trust me, Taiwan is a friendly country. And all right, there's no Chinese people here. Taiwan is kind of different from China. Okay, yeah, it's very important. Yeah, we are more friendly. We are more friendly, polite and friendly, and more has more culture. It's my opinion. Okay, but anyway, there's no Chinese people here, so I don't care about it. Okay. So anyway, you are very welcome to join us. Thank you very much. Thank you for your attention. Thank you. Okay, so maybe it's lunchtime or Q&A session. This depends on you. Okay.
Thank you, sir, for sharing your informative work and ideas with us. So now we are moving towards our next lecture, that is on phased array antenna measurements using a multi-channel receiver test technology. For chairing this session, I would like to invite Shri Arvind Dikshitji, who is CEO and Director of Advanced Technologies Group. Arvind sir, please. So with the kind consent of Chairman sir for this session, I request Mr. Vishal Gupta from Agilent Agmetal to please come for the talk.
I bring the microphone.
And before that, I would like to introduce Mr. Vishal Gupta. He is Senior Applicant Consultant at Agilent Technologies, New Delhi area. He is PGDBM, MBA part-time in marketing, MTech in microwave electronics. He has a vast industrial experience of 15 years in microwave electronics and RF engineering. So I request Mr. Vishal Gupta, please proceed. Thank you.
Afternoon, ladies and gentlemen. My name is Vishal Gupta and work as an application consultant with Agilent Technologies. And my primary focus is on high-frequency test and measurement equipments, and I support all the high-frequency test and measurement equipments from Agilent Technologies. I've been with Agilent Technologies for almost 10 years now, and in the industry for almost 15 years, with my prior experience in RF design, and then to the application support on Agilent products. So today's topic, I'm going to talk about the phased array antenna measurements using multi-channel receiver. The previous paper, the professor was talking about phased arrays. So, from that aspect itself, we can think of, the phased array technology is moving ahead and is getting hot and hot, day by day. Reason being, it's simple because the phased array antennas give you a lot of flexibility in terms of the beam forming, beam switching, not many flexibilities otherwise as well. And that is why more and more phased array antennas have been integrated into different kind of applications, be it satellite application or be it radar application, so that you can steer the beam, you can switch the beams, you can cover different geographical areas by beam forming, from a satellite, or maybe when you have a stationary antenna, you can still cover a lot of geographical region without actually mechanically moving these antennas. So this is going to be the agenda for rest of the 45 minutes which have been given now, because I've been asked to finish by around 1:30. That's fine. So the agenda is going to be, I'm going to cover a little bit upon the phased array applications, the overview of the phased array application, then testing multi-emitter antenna elements. How can we test the element arrays elements? I'll give you different topologies, how these kind of antenna elements can be tested. I will talk about configuring a test system. Being from a test and measurement company, I cannot leave the code of my application. So I'll talk about configuring a test system so that you can speed it up, you can optimize, you can accurately measure a phased array antenna using a multi-receiver technology. Then in the end, I'll talk about how do you realize such solutions. So I'll introduce to a solution based upon the multi-receivers. The model number is given on this particular slide, which is N9703A. I'll introduce to this particular product in a while. However, I'll give you an overview of the technologies, how such kind of a digitizer will help you in such applications. I'll introduce you to a concept called a digital downconverter and how you can leverage from such applications to test these kind of complex antennas like multi-active phased array antennas. I'll little bit touch upon the block diagram, and in the end, if the time permits, we'll take the measurement example, and then we'll consolidate. I'll give you slight overview on the products which we have on our DGSND platform. Right, so let's get started with the antenna applications. So this particular slide gives you overview of various kind of antennas. If I retrospect, myself, the technology, parabolic dish antennas used to dominate the antenna technology. Reason was very simple. They are simpler to make, and the technology, there was no technology available to steer the beam at that point of time. And then we had a mechanically steerable antennas available when we started moving these antennas to cover a more geographical area. And then people switched on to a phased array antenna. And these are passive phased array antennas. What is a passive phased array antenna? A passive phased array antenna will have a phase element wherein the phase of each of the elements can be varied, and then you can control the beam, and you can shape the beam, you can steer the beam from the passive components for the phase element. And then people moved on further, and they introduced the technology of active electronically steerable antenna. In short, it's called as ISA. Right? So what is an ISA? ISA is a phased array element, like the one you are seeing in a PESA, which is a passive electronically steerable antenna. But here you have active elements behind each of the array elements. What is this active element doing? These elements are called as TR modules, or transmit and receive modules. These modules have an individual amplifier of its own and phase element of its own. So you can change the phase, you can increase or decrease the gain of each of the elements, you can switch off the element to configure the beam, you could to shape up the beam, to steer the beam, and many other aspects. Right. So what are the key benefits that you get from an active electronically steerable antenna? One is the antenna can be fixed. So if you have a satellite with an electronically steerable antenna, the antenna needs to be fixed. There is no motorable element now available in the antenna. So in case you want to steer the beam onto this side, okay, in the past we used to move this particular antenna towards this side so that I can cover this in case the pencil beam is to be covered, in case this particular region is to be covered. And I don't want to cover this particular region, right? When I want to cover this particular region, I need to mechanically move it this way. However, using an active electronically steerable antenna is going to be fixed. So there is no mechanical part, there is no mechanical vulnerable part in this. So I have this antenna fixed, and then by changing certain electronic circuitry, the electronic circuitry inside, by reconfiguring the electronic circuitry behind this particular antenna, I can steer the beam this way without actually moving this particular antenna. Okay, so that's what we say here. It has the ability to form multiple agile beams, right? So you can switch on certain elements, you can switch off certain elements, you can increase the gain of certain elements, decrease the certain of gain other elements, change the phase of each of them with respect to each other, and then you are able to configure multiple beams dynamically into the space. Communicate with multiple spatially distributed ground stations. So in case you want to cover, so your mission requires that you need to cover various ground stations, and in between you need not to cover. So you can cover various geographical regions with various other missions, and then you can communicate from the same antenna. Independent transmit and receive modules are there per element, as I just mentioned. How does it benefit you? It also benefits you to reduce power loss from the integration of the RF source on each transmitter. So what happens in case you are having a dish, right, or in case you are having a passive element? This is being driven by a single amplifier behind. Now, in case you are having a single amplifier behind, in case that amplifier conks off, or in case that amplifier fails, whole of the mission is struck. However, in this case, because each of the element has its own TR module, has its own amplifier, in case one of the TR module fails, whole of the mission is not struck. You can still use it for without that particular module. And hence, you can have graceful degradation with single source failure, which is not crippling your complete system. Right? So now, let us understand what are the challenges of an active phased array antenna. Right? So we will talk about two challenges. One is the phase and amplitude errors leads to an increase in the side lobe levels. So in case each of the element is not correctly configured, what happens? I want to have a pencil beam lobe. However, what I am getting is something like this, wherein I have a pencil beam lobe, but then at the same time I am having certain side lobes. Now these side lobes, what are they doing? These side lobes are degrading my performance of the antenna of my system. Reason being, first of all, the power which I am supposed to transmit in this particular direction, I am now transmitting in this direction also. So I am sharing this power into this direction. So this power is lost, this power is reduced. Secondly, if I am going to use it in the receive side, I am going to get a lot of noise on these sides. I am not interested in these interference or in these noise. So I want to reduce all these side lobes, and hence these large single side lobes indicate a waste of beam forming power and may cause interference. Right. Next point. This has been a challenge for quite a while, but then what is a growing challenge? As I said, the antennas are getting more and more complex. Complex in the sense that the antenna elements are getting more and more. There are antennas, phased array antennas available with hundreds and thousands of elements, and people are talking, about single antenna with maybe around 2 million arrays, 2 million antenna elements with around 2 million TR modules in them. Now, how do we test accurately such a system? I have a customer who is testing an antenna that's actually a passive electronically steerable antenna. And it takes him around 2 months to test that particular antenna. 2 months to test one antenna. That is to go into a radar. And in case he has to deliver 8 radars like this, he can at most cover, he can at most test 6 antennas in 1 year. Either he need to have parallel lines, again increase in cost, increase in manpower cost, increase in capital cost, or he needs to devise a system wherein he can fasten the test process. And that is what I am going to tell you today. When I want to fasten the test process, I also want to maintain my accuracy, right? So in that sense, these growing challenges are becoming more and more day by day, especially in the case of electronically steerable antennas. How electronically steerable antennas further complicate the situation. There are TR modules at back, behind each of the antenna element. Now these TR modules also needs to be characterized with different phase characteristics, with different attenuator characteristics or amplification characteristics. Maybe from the transmit side and also in the reverse side, which is the receive side. And then the radars or these satellite applications are getting more and more complex. More and more complex in the sense, now we are not talking about narrow band signals. We are talking about wide band signals, because radar applications are using IQ modulated signals with very wide band, maybe LFM chirp, maybe IQ modulated, maybe marker coded pulses, etc. And in satellites, people are going towards more and more wider bandwidths, maybe hundreds of megahertz of bandwidth. And in case you have to test these antennas for such applications, it requires a lot of deliverance. So what is it? Broadband modulated signals, which are not just pulse signals. You need to generate and capture full bandwidth signals, which means you require such a system. We can have wide band signal capture techniques. So such applications could be synthetic aperture radars, or maybe satellite communication, or maybe other communication systems. Okay. Now let us talk about testing a multi-element array antenna using wherein we will mainly focus upon gain and phase measurements of such elements. Now, in case I want to measure these elements, I am interested in measuring what is my relative gain and phase of each of the elements. That's where, in case I can calibrate the system, I can calibrate my antenna system such that I can find out what is the relative gain and phase of each of the element. Then I can calibrate my system so that I can maintain my beam forming accurately. I can maintain my beam switching, I can maintain my beam steering accurately. Otherwise, as was suggested earlier, we will end up having side lobes and unwanted interference. Right? So there are two approaches for such application, what we call as a narrowband approach and a wideband approach. A narrowband approach, a question for the audience here. How many of you use a network analyzer for antenna measurement? Network analyzer for antenna measurements. That's the oldest technique. That's the most prevalent technique for doing an antenna testing. A network analyzer is used for antenna testing, for its radiation pattern testing, for its gain or directivity testing, in an anechoic chamber or maybe in a far side. We are talking about a different concept, and that's what has been shown here. A network analyzer are limited to narrowband measurements, because network analyzer are based upon narrowband receivers. And in case I want to test a device, an antenna system which is supposed to take care of wideband signals, then I am not getting a real-time stimulus response of my antenna. And in case I want to get a real-time response of my antenna, I need to have a system which can handle these wideband signals. And that's what we say here. Narrowband approach is normally a swept or stepped tone response. It has a narrowband receiver like a vector network analyzer. It measures only one frequency at a time. That means it sweeps the frequency or steps the frequency and measures only one frequency at a time. Lower variance, you can lower the variance. That means you can lower your, you can minimize your accuracy. You can minimize your deviation from the measurement from the desired results by integrating longer. That means reducing your resolution bandwidth or IF bandwidth. What is a broadband approach? The broadband approach means you're giving a broadband stimulus, and then when you're giving a broadband stimulus, you need to capture whole of the broadband stimulus, so you require a broadband receiver. When you are having a broadband receiver, you capture all the frequencies together. When you capture all the frequencies together, you are able to compute cross-channel spectrum. So we get the complete cross-channel spectrum, and hence by averaging this particular cross-channel spectrum, we can improve the accuracy of the measurements. Okay. Now I'll introduce you to one more concept called as digital down converter. Now how can we configure such a system? Okay. So what is a digital down converter? It is a flexible processing block that allows a digital that allows an A to D converter to run at full rate while the output sample rate and bandwidth are optimized to match the current signal. And this is the block diagram shown for a digital down converter. So just after you have digitized the signal, we mix it with a local oscillator, a digital local oscillator. By forcing these digital local oscillator, which are 90° out of phase. So once we mix it with the local oscillator, and another time we mix this local oscillator, which is 90° out of phase, digitally. Then we decimate these samples, and then we sample these decimated samples. We capture into the DDC memory. These captured DDC memory signals we then process and then compute the response which are relative to each other. So what does DDC does for me? What does the digital down converter does for me? So let us take an example of this particular signal. Now this is the signal of my interest. What do I do here is, in this digital down converter, once I mix it, I basically take only the block which has been mentioned into this particular red dotted lines. Okay, so how does it improve my system performance? It improves the signal to noise ratio, because when I am only taking this particular, it is like filtering. It is like digital filtering. I am improving the noise, the signal to noise ratio of my system, and all the unwanted signals like has been shown here. So it also extends the amount of data that I am capturing by reducing the sample rate or by reducing the bandwidth of my signal being captured. So it reduces the workload on the post-processing algorithm because you have less data to process. So an example has been shown here. So in case this is the signal that you want to process, this is the signal that you want to sample, after you have down converted this, it comes to around DC value, right? So I mix it with the same LO of the same frequency. I get the frequency, the baseband signal, which I sample. So I sample it around the baseband, and hence I will be able to reduce it. So the bandwidth earlier, which was around 800 megahertz, by digital down conversion, I am able to reduce this particular bandwidth up to 100 megahertz. And when I am having 100 megahertz of bandwidth, as per the Nyquist criteria, I need to sample it only at the double the rate, right? So as per 800 megahertz, I have to sample it at around at least 1600 mega samples, whereas in this case, at least 200 mega samples. So in I am able to optimize my memory and also the calculation algorithm. That's what has been shown here on this particular slide. Now this is the comparison of a narrowband mode with respect to the wideband response method. So narrowband mode method is almost familiar to everyone, which is based upon the traditional network analyzers, wherein we are sweeping the frequency and sampling the frequency and then getting the response with respect to each frequency. In the narrowband mode, the tones used in the narrowband mode have 0 dB peak to average ratio with all of the source power at one frequency. Normally, the narrowband response method gives you better dynamic range, because the network analyzers mostly have a good dynamic range, and you are having 0 dB peak to average ratio. The narrowband RPW may have long setting times. In case you take a very small IF bandwidth or resolution bandwidth, it takes longer time to sweep. So that's a slow process. However, in the case of wideband signals, which can be almost anything provided there are energy at the frequencies of interest, what do we get? Even at the DUT generated noise, you can use chirps for 0 dB peak to average ratio and lower spectrum density than at the tone. So what does wideband signal does? It gives you DUT type of signal. It mimics your DUT. So wideband signals that mimic the DUT may be more DUT friendly in the measurement application, because you are getting a real-time kind of a signal as if they are coming in from your system. So for narrow band resolution bandwidth, wideband measurements may be faster as all frequencies are captured in the parallel. However, there are many variables such as the data transfer time and number of averages that also needs to be considered. So when we are talking about data transfer, in case we are sampling wide signals, then we need to be sensitive enough that all the data needs to be transferred simultaneously into the memory to be processed. Okay, now let us talk about how do we configure such a system. So this is an example of a system shown to you, wherein you have a DUT, which is your multi-phase array. After this, maybe you are having certain signal conditioning system, which could be attenuators. Then you are having down converters, the digital down converters, and then maybe the digitizer. In between, you are having certain other signal conditioning system, which may be amplifiers or filters. So herein we are showing a multi-channel receiver to do the same job. Now this is an 8-channel input receiver, so that simultaneously you can have 8 receiver inputs with sufficient 3 dB analog bandwidth, providing the facility of digital down converter as was already mentioned, giving you advantages of the digital down converter which have been already mentioned. It gives you phase coherent inputs of less than 1 degree phase drift. Now, if I talk about this particular digitizer, it is having, after calibration, it is giving you 30 picoseconds of variation between each channel. Now, 30 picoseconds of deviation, difference between the two channels at 300 megahertz is around 3.5 degrees. And that is static. So once you have calibrated the system, that's fixed. That means it can be calibrated out at a, when you are doing the measurement of your system. Hence, it is a scalable platform and it is a modular platform. So now let us understand the signal path analysis. Cable losses along the signal path, which vary depending. So if I talk about measuring such a system, measuring such a phased array element, there are two types of inaccuracies in them. One are static accuracies, one could be dynamic accuracies. Static accuracies may be because of the system design, the components that you have used. Once the system has been designed, manufactured in place, those accuracies are going to remain there. So they're static accuracies. However, there are certain dynamic accuracies. That means they vary with respect to time. It could be because of the temperature variation, it could be because of humidity variation, and maybe certain other variations into the system. Okay. Now, how you take care of such two inaccuracies into the system? Static accuracies. As I said, once the system is designed, they are fixed. If you measure them, you can calibrate out these things. Dynamic accuracies. By recalibrating the system under the same conditions, you get the same kind of accuracy as with respect to the static accuracies. Now, for such a system, you can also find out, what is going to be a signal to noise ratio. So this is the first formula given, and then you can understand the signal to noise ratio and absolute power level that is going to reach at the digitizer, so that you can know what is the level of signals with which I'm going to receive at my digitizer input, so that I can judge that what is the characteristics of the receiver, what are the attributes of the receiver I need to set, so that I can use the complete dynamic range of my ADC, so that I sample the signals with the absolute signal to noise ratio. So to do this, we have two methods. One is called the sign fit method, the other is called the DDC method. Now the digital down converters can also be used using the software techniques. Now the digital down converter can also be implemented using the software. Right, so that's what I said. Uses complex samples complex conjugate ratio method cancels the common mode phase and modulation. Your sign fit method is mathematically sign fit to the single tone samples. It is based upon the IEEE basic test methods for digitizers, and it is relatively slow as compared to the digital long converter. This particular system shows you that a channel receiver being fed by a signal generator and then being triggered by a function generator. And now let us see that after calibration, what are the values we are going to get. When we are feeding an input power of 6.5 dBm from channel 1 to channel 3, I am getting around this much of variance. These are the variance values for sine fit method and for DDC method. So this is around 4.81 into 10 to the power minus 0.6 seconds. In case of this DDC method, it is 5.49 e raised to the power minus 26 seconds square. Now you can see here that your skew variance is much better in at lower frequencies using the DDC method, and at higher frequencies or at lower values of power using the sine fit method. Now these are certain questions that the user of the system needs to deliberate upon while configuring this particular system. How accurate is good enough for me, so that I can know that what are the signal conditioning system I need to use, and I can optimize on my cost. And what is your IR center frequency is your IR bandwidth. Whether you want to use the digital on converter or not. Whether you would like to use 8 channels or more than 8 channels. What software environment are you using? Whether you're using MATLAB or whether you're using certain other customized software to sample these signals. And do you have data on complex frequency response for all the signal path that blocks out to the calibration reference frame? I'll introduce you one more software here which can give you channel response with respect to each other, which we call as a vector signal analyzer software in a short while. Okay, so now let us focus on this particular receiver which I'm going to talk about, which is an 8-channel receiver. This is M9703A 8-channel AXI platform receiver. Now this is based upon the newest modular platform called AXI, which is having a 12-bit resolution up to 8 channels sampled at 1.6 gigasamples per second. You have an interleaving option to up to 4 channels, which wherein you can get up to 3.2 gigasamples per second of sampling rate. You have an optional real-time digital down conversion on 8 phase coherent channels and up to 256 megasample channel memory and segment data. You get the data transfer at a very fast speed up to 650 megasamples per second, megabits per second. It also supports the industry standard BSS software called 89600, wherein you can do 8 channels of sample and then compare each of the channels and get the frequency response of each of the channels with respect to each other. So that's what has been shown here. These are the screenshots of the BSS software, wherein 3PSA modulated, 256 modulated waveform has been fed at the elements, and then you're getting the frequency response of each of these with respect to each other. This also shows you the effective number of bits per channel. At 48 megahertz, it is around 8.7 typically bits. At 100 megahertz bandwidth, it is around 8.8 bits. And at 400 megahertz, it is around 8.2 bits. You get an absolute good spurious-free dynamic range when you use this, which is up to 60 dBc at 100 megahertz. This particular slide shows you the DDC feature and their benefits, which have already been talked about, so I will not spend much time on it. Now, the memory which I talked about, the 256 megasamples of memory inside, this is a segmented memory. Now, what does a segmented memory means? Now, this memory has been divided into different segments, and it works in a round-robin fashion. So, in case I say that 256 megasamples of memory, I segment it into 8 segments, right? I will fill up one of the segment first, second segment, third segment, fourth segment, fifth segment, and it keeps on filling it like this. and then I keep on vacating the first segment. So it is like toggling from first to second. I fill up the second one, second to third, I move the first one to second, and likewise. And then it is going like this. So it is like P4, first in, first out. So I keep on filling like this, and it is like going in the round robin fashion. And then you can optimize the usage of this particular memory. So longer duration of acquisition can be done in the round robin fashion, like the one has been shown here. So you can accelerate your test time with the fewer samples in such cases. Talking about the VSS software, the VSS software can control this particular digitizer, which gives you a seamless control of M9307, M9703 digitizers. It also recognizes a digital down converter, supported spans, supports the IF magnitude trigger, which is required for triggering each of the channels, and it gives you multi-channel support up to 8 channels. So this is a picture of the hardware shown here, wherein we have these 8 channels, and what we are showcasing here is we are feeding one of the signal from here, which is a single tone signal, dividing it into from this 8 channel divider and feeding it into for the calibration purpose. So all these cables are phase mesh cables, and then we are calibrating this particular system, and after calibration, as I mentioned, we are able to achieve up to 30 picoseconds of inter-channel skew, which is around 3.5 degrees or 300 megahertz. This is an example shown for the SATCOM 256 QAM signal. So just to summarize, the Agilent M9703A digitizer with the digital down converter can be a solution for multi-antenna array measurements, which provides you the benefits of multi-channel measurement solutions with less than 1 degree of accuracy between the channels, fast and adjustable bandwidths, measurements producing complex samples with just enough sampling rate so that you can optimize upon your memory, integrating the industry standard VSS software with the digital down conversion acceleration to leverage wealth of existing industry standard measurement. Now, this is what I wanted to share with you on the measurement platform. Now, I'll take 10 more minutes before I finish my time of around 1:30, wherein I'll talk about of other products which we have on the DGSND rate contract platform. So what is DGSND? DGSND is an establishment, it's a Government of India establishment which does the rate contract with various vendors for certain products which are more used by the Government of India users. Now from Agilent side, what we have in this particular rate contract. So let us assume this is my device under test. Now a device under test, electronic device under test requires 2 things. What are these 2 things? A stimulus and a response measurement and an analyzer. Something we can generate the stimulus and something which can capture the stimulus output of my device. So that's what we say here. On the left hand side, we have the list of all the stimulus generators, which could be a DC power supply, which could be a pulse generator, a function generator, a arbitrary waveform generator, a CW signal generator, a vector signal generator, and likewise many other kind of platforms. On the other side, we have all the measurements, all the instruments which can capture the output response of these devices, which can be a logic state analyzer if I talk about the digital interface, which can be oscilloscopes if I talk about IF or analog interface, which can be a vector network analyzer, which can be a signal analyzer if I talk about the RF and microwave, which can be digitizers, multimeters, etc. Now we have the general purpose equipments on the rate contract, which could be our handheld series of oscilloscopes, programmable DC power supplies, clamp meters or multimeters, frequency counters. We have function generators on the generator side, on the general purpose function generators and signal generators. So we have vector signal generators up to 6 GHz, analog signal generators up to 40 GHz on the DGSND rate contract. Now you must be wondering why I'm talking about DGSND rate contract. The idea is very simple. It simplifies your procurement process. You need not to do any tendering, you need not to do any specifications. All the things has been done a priori by DGSND, which is the Government of India body. They have done all the tendering, they have specified the products which are general in nature, and then they have optimized on the cost, and then they have done the rate contract with each of the vendors. So we have a 30 megahertz function generator, we have a 6 gigahertz vector signal generator, we have 20 and 40 gigahertz analog signal generators on the digital rate contract. We also have 3 and 6 gigahertz analog signal generators on the rate contract. Then we have our high-end signal analyzers, which we call as, in earlier days, which we used to call as spectrum analyzers. Now we call them signal analyzer, wherein they can do much more than a spectrum analyzer. So we have these high-end signal analyzers on our rate contract, the PXA series of signal analyzer, which is our highest performance signal analyzer, and which is actually the industry's highest performance signal analyzer, with up to 160 megahertz of analysis bandwidth on digital rate contract, which is upgradable to real-time spectrum analysis capability, giving you a dynamic, displayed average noise level, a sensitivity of up to minus 172 dBm at 2 gigahertz, which is almost just 2 dB above the thermal noise floor. Giving you the best phase noise in the industry, and having many other measurement features which are required for any microwave test lab. Similarly, we have mid-range signal analyzer up to 26.5 gigahertz. So these signal analyzers are available on the digital rate contract at 8.4 gigahertz, 13.6 gigahertz, and 26.5 gigahertz. We have other range of products wherein we have a handheld BNA on the digital rate contract. We also have other kind of signal economy signal generators on the digital rate contract. We have logic analyzers on the digital rate contract. I would like to also mention we have certain test labs as a platform on digital rate contract from Agilent Technologies. What is the test lab? Especially for the educational institutions, these test labs, what are they? A test lab requires a stimulus. A test lab requires a device which is pre-known. A test lab requires certain analyzers. A test lab requires experiments which are pre-written for the students to do in their labs. A test lab requires certain evaluation sheet. A test lab also requires certain teaching material for the professor. So that's what, this is the platform. We have various kind of test labs on the digital rate contract. One is being shown here, which is a multi-purpose lab station for undergraduate students. Then we have RF communication test lab for undergraduate and postgraduate students. Then we have digital RF communication lab for UG and PG students. We have the microwave trainer kit on the rate contract, and also we have a software-defined radio platform on digital rate contract. So with that, I will stop here, and I'm open to questions. Any questions? Yes, sir. Can you repeat the question, sir?
The instrument that you have discussed for phased array measurement.
Yes.
What are the parameters of the array that can be?
We are talking about gain and phase, the relative gain and phase measurements of each of the elements.
Individual elements?
Of each of the elements, yes. That's where you require multiple channels, because you have multiple arrays, multiple elements in the array, and you need to measure how one element is behaving with respect to each other. So you are assuming, as per your design, that they are phase matched. However, they might be different in nature because of the component that you are using. Each component will have a different kind of, its accuracy limits. So they might be deviating by, let's say, 2 or 3 degrees, and you want to calibrate this particular antenna system of each of the element with respect to each other. So that when you want to make the beam, you are not bothered about about the accuracy of each of them, because you have pre-configured that, have that in the calibration table, and you have calibrated your beam calculation with respect to each of the calibrated values. So these are measuring each element with respect to each other. Does that answer the question?
Basically, that is adjustment of the amplitude and phase of the
active elements. So we are mainly talking about the active phased array radars, wherein we have tier modules and the antenna element behind which each of the tier module is kept. So we are talking about each element with respect to each, the other element. So let's say this is my one element, this is my second element, third element, fourth element. So I make the measurement of this with respect to this, with respect to this, with respect to this, with respect to this. So I'm making measurements of each of them. So these are all relative measurements.
You have the option to state the reference
You can, yes. So let's say you want to measure only this element with respect to this one. So then with respect to this, you make this as reference and then make this measurement. Normally how it is done, you make one element reference and keep on measuring with respect to each other. Yes.
Not necessarily be the edge element, it can be anywhere.
It can be any element that you choose. Because we want to calibrate whole of the system. Any other questions? Yes, ma'am.
So I just wanted to know how much simulation time it will take for, let's say, a 10 element phased array. I mean, what is the relation between the simulation time and n element array after the technique you have specified?
Okay, so this is a good question. So I mentioned about speed, and a customer who is doing testing of, let's say, 5,000 elements, around 4,800 elements, and he's taking a month to calibrate all of the antenna system. If you're using such a system and you have written and you're using a software to do this, it can be, so this 4,800 elements can be done within a day. That kind of a speed we are talking about.
All right, thank you.
Is there a question? So if there are no more questions, I'll stop it here and thank you all for being patient and giving me an opportunity to present. Thank you.
Thank you for your presentation. Let's go for another session.
Thank you, Arvind Dikshit sir. Thank you, Vishal Gupta sir, for keeping our request of time limit. Now I request all the participants and delegates to please move for the lunch. Now this is for the information of all, and please convey this to your friends also, that today we are going to reduce the lunch time by half an hour. Means now the lunch time is from 1:30 to 2 p.m. as we have to cover the pending participants presentation for the S1 session today only. Thank you.